fiat lux. In this video lesson, we're going to talk about electromagnetic radiation, including what we commonly call light. And we will see that light is just a portion of the spectrum of electromagnetic radiation. To quickly review what we've been covering waves. We've talked about compression or longitudinal waves, which include sound. We've talked about transverse waves. We have discussed the speed of sound, 340 meters per second, and how sound actually moves more rapidly in solids and in liquids, and then actually moves most slowly in air or in gases. In the last video lecture, we talked a little bit about music and hearing. We mentioned how human beings can hear frequencies ranging from the very long wavelength, low frequency, 20 hertz frequency sound, which corresponds to wavelengths as long as 17 meters, to the very high frequency, short wavelength sound as short as 1.7 centimeters, just about twice the width of your fingernail. And how our ears are this exquisitely designed organ which can sense the compression waves in air, which we then recognize as sound. A couple of other properties of waves which we talked about were the phenomenon of interference, in which waves can either add together constructively or they can add together destructively, or essentially cancel each other out. And we also talked about the Doppler effect. So in this video lesson and in the next, we will focus on electromagnetic radiation or light, the special type of waves. Well, what is an electromagnetic wave? What is light? An electromagnetic wave is energy that can travel even in the absence of a medium, meaning that it can travel even through a vacuum. Now, electromagnetic waves and light can travel through solids such as glass or liquids such as water, and of course through gases such as air. But an electromagnetic wave can also travel through a vacuum. That is, it does not need a carrier. Now, this was difficult for scientists to understand, and in fact, early scientists thought that light must travel through some substance. They hypothesized that there was some substance in outer space, what they called an ether, through which light traveled as a wave. And it took scientists a long time to actually come to our current understanding of electromagnetic waves. And in fact, if you find this a little challenging, it is. We will see in the next slide that an electromagnetic wave is actually two waves. One which we'll call an electric wave and the other a magnetic wave, and they travel perpendicular to one another. An important feature of electromagnetic waves is that it moves with a velocity of 3 times 10 to the 8th meters per second. And in fact, light, or an electromagnetic wave, moves as rapidly as is physically possible. Now, 3 times 10 to the 8th meters per second corresponds to 186,000 miles per second. This is what we call the speed of light. Now, to give you an idea, the Earth is 93 million miles from the sun. It takes a little over 8 minutes for light from the sun to travel to Earth. Now, think about that. What that means is if the sun had exploded a little less than 8 minutes ago, we wouldn't know about it yet, because it would take 8 minutes for the light to actually reach us on planet Earth. And that tells you something about the great distances, but also about the speed of light. We also mentioned earlier when we talked about dimensions, about how the meter itself is actually now defined in terms of the speed of light. The speed of light is a fundamental universal constant. Universal meaning that in a universe, that the speed of light would be this number, as fast as anything can possibly move. We will see in a few slides the entire electromagnetic spectrum. The region of the electromagnetic spectrum that we focus on is what we call visible light. It's what we can see. And it turns out that visible light ranges from red light, which is the longest wavelength, 600 to 700 nanometers, to the shortest violet or blue, which is around 400 nanometers. We'll get to that in a little later. In subsequent lectures, we will talk about what actually produces an electromagnetic wave, and we will talk about how it is produced by a moving electric charge, but more about that later on. I said a minute or so ago that an electromagnetic wave actually involves a sinusoidally oscillating electrical and magnetic component. This is shown in the bottom left, where the electric component, given by the letter E or E field, is in blue, and it is oscillating in a sinusoidal manner. And then in red, there is a magnetic component, or magnetic field, and notice that it's 90 degrees or perpendicular to the electric field. And these two are oscillating together. That's a little hard to visualize, so let me show you this animation. To try to understand this animation, if you look sort of in the middle where you have a larger red and blue arrows, and you can see that as the wave is propagating, the red electric vector is going up and down, oscillating in a sinusoidal manner, and then to its left and right, the blue, notice that they changed the color scheme for some reason, that the blue magnetic vector is going left and right. So this is how we now envision a propagating electromagnetic wave. So it is a wave, but also an electromagnetic radiation, in some cases, behaves as if it's a particle or something like a particle. And so we have to have a word for this. We call this a photon. A photon is the smallest packet of electromagnetic radiation, the smallest amount. In later lessons, we will talk about the duality, the dual particle and wave nature of electromagnetic radiation, how it sometimes acts as if it's a wave and sometimes acts as if it's a very, very small particle called a photon. With sound waves, we talked about how two waves of the same frequency could add together either constructively, which is what we would normally expect it to happen, or destructively, that is, it could actually cancel out. Light can show such constructive and destructive interference as well, and we will be talking about some classical experiments that were used to help us understand the behavior of light. The slide shows the basics of one of those types of experiments called a double slit experiment. To the left, we have a propagation of electromagnetic radiation that's in the parallel lines that are supposed to represent the peaks of an oscillating wave coming towards the blue barrier. And imagine having two slits or two openings in the barrier so that the light can only go through those barriers when it passes through those two small slits. When light passes through an individual opening or an individual hole, it will be diffracted or spread out. And if you have two slits, there will be a resulting areas in which there will be constructive interference and destructive interference for the light passing through these two holes. The result will be a pattern, what is called an interference pattern, which is shown on the right, which shows alternate regions of high intensity of light and then the absence of light, high intensity and the absence of light. This is a result of the property of waves being able to either add together constructively or interfere with each other. We also talked about the Doppler shifts or the Doppler effect with sound waves. The same thing applies with light, with electromagnetic radiation. And we mentioned that this is used to determine if stars or galaxies are actually moving towards planet Earth or away from planet Earth. On the left in this drawing is our blue marble, planet Earth. And to the right is some spinning galaxy. And the middle and bottom drawing are for galaxies that are moving away from planet Earth or moving towards planet Earth. And as with the Doppler effect in sound, if the galaxy is moving away, there would be a red shift in the light that we detect from that galaxy. If the galaxy is moving towards us, there would be a blue shift in the light that we detect from that galaxy. This shows you that the wave behaviors that apply to sound also apply to light. Now, another property of light is that it is polarized. This is a fairly complicated topic, and I'll just try to explain to you those aspects that should be of interest to you. Most light sources produce light that is polarized in all directions. Now, what that means is that the electronic vector, the one that's oscillating up and down, is also oscillating at every possible angle and not just in a vertical direction. And that's what's shown as to the left. If you have a polarizer, and you can imagine a polarizer as a filter which only allows light that is polarized along one axis, such as the long axis of those slits. So that if light passes through this polarizer, only light that is vertically polarized would go through those vertical slits. Okay, well, what if you have two of these filters, two of these polarizer filters, and you oriented them perpendicular with respect to each other? What would you expect? Well, if the original light source is polarized in all directions, as shown to the left, and if you first have a vertical polarizer, it would only allow light that's vertically polarized to go through. But if the next polarizer or filter is oriented horizontally, you would predict that it would block the light completely from traveling through the second polarizer. And that's more or less what we see. Now, this may seem like a very esoteric property of light, but it turns out it's something that is relevant to our daily lives, because many of you will have a pair of Polaroid sunglasses. Yes, these polarizers or filters that I've been talking about turn out to be the lenses for Polaroid glasses. And as in my examples on the left, if you have light that is oriented vertically and horizontally and every angle in between, the Polaroid filters will only allow light along one axis, let's say vertically polarized light, to come through. So this will greatly diminish the intensity of the light that is coming through, but also will minimize glare. Now, if you've ever had a pair of broken sunglasses, and I'm not advocating that you go out and break your pair of sunglasses, but if you ever do have a pair of broken Polaroid sunglasses and you take the two lenses and you hold them up and you look at a light source like the light in your room, and then if you rotate one of them 90 degrees with respect to the other, you will see that the light intensity that goes through those two lenses diminishes greatly. It may not go to zero, but it diminishes greatly. Now, to give you an example of the effect of these polarizing lenses, I show some examples where on the left you see a photograph without Polaroid lenses, and on the right there is a view looking through polarizing lenses. I like the one that shows the cat the best. It seems to be that one. It seems to be the best example. I usually don't wear sunglasses because everyone else in my family seems to look good in a pair of Polaroid sunglasses, but not me. I just don't look cool. Oh, we're going to pause now and have a quiz, and then we'll continue on and discuss some additional properties of light. Okay. Just can't look that cool with Polaroid sunglasses. That doesn't work for me.